These are the video notes for Objective 4A, Solving Systems of Nonlinear Equations. The first two examples we want to solve using what's called the substitution method, and the next two examples we're going to try using what's called the elimination method. However, you can use any method of solving a system of equations on any assignments or tests. So to make the substitution method work, you need to identify an isolated variable, such as this y in the equation y equals. If you can't find an isolated variable, you have to make an isolated variable. Once you've identified the isolated variable, you can substitute that expression into the other equation for the value of y. After substitution, your new equation is x plus x squared minus 6x plus 9 equals 5. So we have x plus our substituted expression is equal to 5. Now we have a single equation with a single variable that we can solve. Combine like terms. And we also want to subtract the 5 over to this side. In an ideal situation, the expression we're left with is factorable, which it is in this case. We're looking for numbers that multiply to be 4 that can add to be negative 5. So our two solutions are 4 and 1. However, the solution to a system of equations has to be an ordered pair that represents where the two equations intersect. So I have two intersections, we'll call them x1 and x2, and I have to find two coordinating y values. So we'll take this 4 and we'll plug it in for x. And we could have used either equation. I ended up choosing the first one, although the second one was probably easier. I've got 16 plus 9 minus 24 is 1. And so my first answer, x1, y1, is 4, 1. Then I need to plug in 1 to either equation. So let's try the second equation. 1 plus y is equal to 5. So y equals 4. My other equation is 1, 4. So my two solutions are 4, 1 and 1, 4. For example 2, we don't have something perfectly set up for substitution right away, and we're going to have to solve for one of our two variables. And so in this setup, what we're looking at is the equation of a parabola and the equation of a circle. Now, you don't need to know that until we start solving systems by graphing, but just keep in mind that these are both non-linear shapes. So here, I have an x that's almost by itself, and I can rewrite it as x equals 6 minus y squared. And then I can substitute that in for x into the other equation. And so I'm left with 6 minus y squared plus y squared equals 26. This squared means I need to multiply it to itself with full distribution, no shortcuts. And that gets me 36 minus 12y squared plus y to the 4th plus another y squared equals 26. Bring everything to one side and rearrange it. So I'm going to have y to the 4th minus 11y squared plus 10 equals 0. This expression is factorable. So I have y squared minus 10 and y squared minus 1 equals 0. That gives me a first answer of plus or minus the square root of 10 and a second answer of plus or minus 1. What's interesting to note with this problem is that there are 4 answers to this system. That means that this equation when graphed and this equation when graphed will intersect each other a total of 4 times. And feel free to check this on a graphing calculator or on Desmos just to confirm. But let's break out all of our answers. We have y1 equals rad 10, y2 equals negative rad 10, y3 equals 1, and y4 equals negative 1. Plugging each of these back in, it appears that this equation is going to be the easiest because it's already solved for x. So I'm going to say that x1 is equal to 6 minus the square root of 10 squared. That means x1 is equal to 6 minus 10, which means that x1 is equal to negative 4. My first solution is negative 4, rad 10. Repeat this process with each of your solutions. Notice my use of parentheses because this does have an effect on your answer. Again, I get negative 4. Over here, for x3, I have 6 minus 1 squared, which is 5. And for the last one, I'm going to do x to the 4, or x4 is equal to 6 minus negative 1 squared, and because of the parenthesis, this is also 5. All 4 solutions down at the bottom, written as an ordered pair. For our next example, we're going to use the elimination method to find the solutions to a nonlinear system. The elimination method requires that all of your terms align. If they're not aligned, you have to align them. And then the goal is to get one of the variables to eliminate by adding the equations together. So looking at my first equation, it appears that I should be able to eliminate the y's. I won't be able to eliminate the x's because the second equation has an x squared term and a linear term, and the first equation only has a linear term. If I want to eliminate these, I need to change the signs of the second equation. Negative, negative, positive, negative. And then these terms don't line up, so I want to rewrite this system off to the side. Y equals space or 0x squared plus 5x minus 20. And underneath, negative y is equal to negative x squared plus 5x minus 5. Add the equations together. The y's will eliminate, which is the point of elimination. Negative x squared plus 10x. And then I prefer, or I need my x squared to be positive, so I'm just going to bring everything to the other side, which leaves me with this equation. And this is factorable. So it multiplies to be 25. They can add to be negative 10. And that gives me the same solution with a multiplicity of 2, which means I really only have one solution to this system of equations. And that solution has an x of 5 and a y of 5. Final answer is the ordered pair 5, 5. Let's try the elimination method one more time. For example 4, we have 5x squared plus 14x plus 1 equals y, and we have negative 12 plus y plus 40x equals 0. If I want these terms to line up, I'm going to need to subtract this y to the other side of this equal sign so that I have 2 y's down here. Since this is already written in standard form, I'm just going to recopy this equation as is. My second equation, I'm going to rearrange and subtract the y. So if you do minus y, I want these expressions to line up with their like terms. So I'm going to put the negative 12 underneath the 1, the 40x underneath the 14x, and then a placeholder under the x squared, all equal to negative y. Since y and negative y are already set up to eliminate, I don't need to multiply this equation by anything. I can just add the expressions together. 5x squared plus 54x minus 11 equals 0. This equation is factorable. I'm looking for numbers that multiply to be negative 55 that can add to be positive 54. And that leaves me with 55 and negative 1. Using my shortcut to factoring, I'm going to write the 5x in both expressions and then divide it out of the first one. My two solutions to this system of equations is x1 equals negative 11 and x2 equals positive 1/5. Plugging these back in, it looks like the second equation would be easier to solve for y. So I'm going to rewrite the second equation as y equals 12 minus 40x, and then I'm going to plug in my x's to this version. That gives me y2 equal to 12 minus 40 times negative 11. y2 equals 452. So, not y2, y1. So my first solution is negative 11, 452. And my second equation, y2, equals 12 minus 40 times 1/5 is y2 equals 4. So my second answer is 1/5, 4. This concludes part 1 of the video notes for solving nonlinear systems of equations. This is actually the only part of the system of equation notes where we're actually going to deal with nonlinear. In part 2, we're just going to apply our system of equation techniques, substitution and elimination, to solving a 3x3 system of equations.